browser so others can
Okay, I
join.
leave it up to you. Yeah, first time is sure. Yeah.
Yes, so greetings and welcome everyone. A warm welcome to all of you to the Asia Pacific Biopesticides Community of Practice.
Uh,
Um,
can you request everyone to be on mute?
Please be mute everyone while you are joining. Yes. Okay, thank you. So, a warm welcome to all of you to the Asia Pacific Biopesticides Committee of Practice, and it is wonderful to see you all here today. So, before we begin, I will quickly give you a recap to the last session. So, last month we held an open forum where everyone from the audience was welcome to speak, and Dr. Ravi introduced the forum and emphasizing the importance of discussing key challenges in biopesticide use. And he outlined six major discussion areas: awareness and use of biopesticide, challenges in production and manufacturing, public-private partnerships, availability of innovative tools for biopesticides, research and development and innovation focus, policy and regulatory framework. So, last time we successfully gathered your insights and perspectives on the biopesticide and biological control, which will be shared in the future. So, with that short intro and the briefing, I would like to now invite Dr. Ravi to deliver the opening remarks and continue the session. Dr. Ravi, over to you, please. Sir, you are on mute.
Thanks, Darshika. I think Dr. Malvika Chaudhary, we have requested her to do the job for this given community of practice because I just joined to greet and thank Dr. Malvika and Dr. Wan Shapalu because I have to leave for Ministry of Foreign Affairs for an urgent work just now. So thank you so much, all of you, for joining. Thank you, Darshika, for organizing again. And Dr. Malvika, over to you.
Okay. Thank you so much, sir. And it is indeed my pleasure to host the this particular session for COP, which has been so useful for the bioprotection practitioner. I'm very happy that Dr. Van Shipalu is with us today. I would like to give a brief introduction to her, as her impressive biodata is right now with me. And I would like to introduce Dr. Van. She's the head of plant pathology and post-plant resistance group at IRI. Her group works on multiple bacterial viral diseases of rice and focuses on the discovery of new disease resistance genes that are useful for improving rice disease resistance. So this is an important crop, as we know. She's also working on the microbiome and beneficial microbes, as her group focuses on identifying beneficial microbes that could improve stress tolerance and host gene controlling the assembly of rice microbiome and beneficial microbes. She is also exploring the possibility of reshaping the microbiome towards enhancement of disease resistance and low methane emission. And before joining IRI, she worked as rice team group leader at the University of Dusseldorf, Germany, where she focused on studying the interaction between rice and leaf blight bacterial pathogen and developing advanced genome editing platforms for rice. So Dr. Van, she did her PhD at the Max Planck Institute for Chemical Ecology, a very well-known institute in Germany, where she studied different layers of plant defense against fungal pathogens, from defensive genes to phytohormone signaling, the production of antifungal secondary metabolites, and also their association of beneficial microbes. So, with this introduction, I would like to welcome Dr. Van and also ask her to continue with her presentation so we all can be enriched by her knowledge. Thank you so much.
Thank you very much, Malvika, for the very nice introduction. And welcome everyone. Thank you very much for joining. I also would like to thank Dr. Ravi for inviting me to this meeting. It's my first time joining the community. And would be very happy and very excited to meet all of you and to learn more about your works and how we can collaborate and work together. Yeah, so I will be talking. Actually, this is my really first time really talking on microbiome because my topic is really mainly on host resistant. So bear with me and I go through some of the slides for the first time. I will start sharing my screen. Um,
Không thì sao rồi?
so if I put this on the presentation, could you please confirm if you can see my screen and can you see my full screen?
Yes, we are seeing
Yes.
Thank you.
Excellent. Thank you very much. So when I was asked for what would be the title for my talk, I immediately thought of, okay, I'm still on the journey of searching for microbial solutions to enhance rice disease resistance. So that's why I first thought of this topic to be explaining what I'm trying to do here at Erie. So I will just give a first introduction into why rice and rice disease are important, and then what are the approach or questions that I'm trying to answer with my current research, and what are the results that we currently have, and some of this perspective for the futures. So I think this slide is really just to put we on the same stage, but I think everyone know that rice is really important. It is not only our food, but also our culture. Rice feeds 4 billion people, so more than half of the world populations, and most of those are from Asia. And rice is also grown by 144 million rice farmers, which is 1/4 of the total world farmers, and 91% of the rice productions is coming from Asia, just to show how important Asia is in terms of rice productions. And rice also bring in an annual values of 206 billion per year, which is 13% of the world's crop values. But rice cultivations is a resource demanding activity. So rice requires a lot of resource. 35% of the world's irrigation waters is for rice cultivation. 10% of the world cropland is for rice cultivation area, and more importantly, we see that rice cultivation consume 15% of the total world fertilizer. Not only so, rice also emit 12% of total methane emissions. And rice cultivation face a lot of challenges. 50% of the total area in Asia are prone to abiotic stresses like drought, salinity, submersion, but also a great number of biotic stresses in tropical and temperate areas. So now come to the area that I really like, and most of the time I talk about is rice diseases. More than 20% of microorganism species or species of microorganism are known to attack our rice plants, and they range from bacteria to fungus, virus, phytoplasma, and some of the major disease what we've seen, I think probably you're familiar with are over here bacteria plague and rice blast. Sheet blight is also considered as a major disease that also occurring almost every year. And Tungros is on an important viral disease in Asia. But we have other diseases that are incoming, and they are considered as emerging diseases that are important as we see the climates are changing. We have changing also in terms of way that we cultivate our rice. So some of the disease that were not that important in the past, but now become more important. For example, brown spot are more prone in direct seeded rice area. Fall smart is really important for a high yielding variety. Hybrid rice, for example, are highly susceptible to this disease. And rice disease in general account for 20-30% yield loss, that enough to feed 70 million people. That a lot of losses that the farmer have to take care. But also in this community, as we know that the use of pesticide, fungicide, bactericides in general harmful or known to some of that, and some extent known to be harmful to the environment but also the human health. And the production of pesticides also account for the global climate change. So the challenge we have to face here is that when we talk about disease, that the pathogen, they evolve much faster than plants. And and then they are microbes, so they migrate without borders. They can migrate quickly, and they don't care if this in another country or not. And we have climate change that affects the disease distribution and also severity. Some area we were not prone to disease before now become more prone to disease, or some of the disease are moving upward to more temperate area. So in order to manage or prevent disease, so there's a classical way that we all study that to manage rice diseases, we need to take care for the disease triangle. So it's always take three to make a disease. The virulent pathogen need to find a susceptible host in the environment which is conducive for the pathogen to thrive. So in order for us to manage the disease, we also have to take care for these three dimensions. For in terms of pathogen, usually we try to avoid area where that prone to diseases, or try to eliminate the source of the pathogen in our field. In terms of host, we are looking at the resistant genes where we can introduce or breed for better resistant varieties. And in terms of the environments, how we do our cultivation practice, water management, fertilizer management, etc., in the way that is favor our plant and unfavor to the pathogen. But we also know that out there not only microbes that are harmful to our plants, they are pathogen, but there are a lot of them that are non-pathogen, and a great number of them are considered to be beneficial microbes. And so if we are able to unlock their potential and utilize them to manage the right disease, we will have much better way of managing our diseases. So actually it would take four. We could try to manipulate the microbial community in the way that it's enhanced the number of beneficial microbes. We could also try to breed for varieties that contain a healthier microbiome, or having genes that would be enabled for the recruitment of beneficial microbes. or we could also manipulate the environment that could also favor the community of beneficial microbes. So I'm trying to think in that 4 dimension right now. So in our group, as I mentioned briefly before, we are working mainly on the host resistance, where we look for disease resistant gene. And of course, in order to look for a suitable resistant gene, we need to take care of the pathogen population. What are they out there? How they attack our plants? But the third component of that is the microbiome and beneficial microbes, which is then considered as a second genome of our plants. So we're trying to look into that and how to have engineering the microbiome toward enhanced disease resistance. So today I will mainly talking about the microbiomes because that fit better to our community. I let out the host resistance as well as a pathologies work. In terms of microbiomes, we are focusing on 3 major questions that we're trying to address. The first question is, how do rice cultivation practice impact its associated microbiome? So in the other word, how nitrogen management or water management could actually impact the rice associated microbiome. Those are either rhizosphere microbiome or soil microbiome. If we know answer for this question, we'll be able to recommend rice cultivation practice that could favor the beneficial microbes. The second question is how the rice host control its own microbial profile. Do we have a genes that the plant use to recruit beneficial microbes or control its own microbial structures? So if we know that gene, we can then breed for a resistant variety with healthier microbiome. And the third question is really about who are the beneficial microbes of rice. If we know what species are they, and if we have their inoculum, we can reintroduce them right into the field. So then I will just walk you through the 3 different studies to address these 3 major questions that I'm trying to answer. So the first questions about the impact of agriculture practice on the microbiome. Here we, the study number 1 we are doing at the moment is to see what is the impact of nitrogen fertilizer on soil and rhizosphere microbial community. We utilize on the left hand side you see this is a EV long-term experiments that were established in the 1962, where we have continuous cropping 3 seasons per year, and we have 4 different fertilizer treatment. So either no fertilizer and then with a 65 kg per hectare or 130, or the one which is very high nitrogen going up to 195 kg per hectare. And then we ask the question of whether those continuous cropping and over so many years and different nitrogen treatment, how is now the difference in terms of the soil and rhizosphere microbial community. So we took our sample from the plant and we subject them to shotgun sequencing, where it's basically sequence everything which is in the sample that account for also bacteria, fungus, etc. And we see, we counted here the number of species. So you see here in the middle, this graph is to show the microbial diversity across different nitrogen treatments on the exit. So you have over here 0 kg, and then going to the right side, you have higher nitrogen treatment. But we also take a look at different soil depth. We have like 0 to 5 centimeter or to 5 to 15 centimeter depth and rhizophyte soil. And you can see that in general, we have some trend. However, there is no significant difference in terms of the microbial diversity across different nitrogen treatment. Interestingly, we see that in the top soil, you see a more fluctuate in terms of the diversity. But overall, there's no significant difference. And when we look into that community and say, okay, maybe the number of species are not different, but certain species are different in terms of abundance. And when we look into the nitrogen fixing bacteria, some of them are plotted out here. We saw some trend that some of them like seem to going up when you have higher nitrogen. So it's like you have more substrate for them to grow. So you have more nitrogen fixing bacteria there in the soil. We also take a look at microbes that can produce salicylic acids that are known to also be able to prime the plant defense or enhance the systemic disease resistance. And comparing some the species are plotted out here and compare across different nitrogen treatment, we didn't see much of a difference across different treatments. Similarly, we look into growth promoting bacteria, bacteria producing IA. For example, we also didn't see much of trend across different fertilizers. So this is still a preliminary data, and we run this for 1 season. There are still 2 more days a season to be analyzed. But it's just the first dry season. Last year, we had this data show that we seem to have no significant difference in terms of some of the beneficial microbes in the rhizophyte community. And in the second study, where we look into what are the whole gene that can impact the rice microbiome. In this case, we have a project with Colorado State University studying on how defensive genes are actually have an impact on the leaf microbiomes. Our hypothesis here were really on some of the sugar transporter gene that responsible for the sugar leakage during the infection of the pathogen might also play a role in controlling the leaf microbiome structures. So we have edited or modified some of those genes, and we are looking at the leaf microbiome profiles, comparing of the line with the modified gene or edited gene compared to the control one, and also with and without the pathogen challenge, what changes in the leaf microbiome we will see. And not only the sugar transporter gene, we are also looking at other downstream defensive genes that are responsible for producing secondary metabolites, defensive secondary metabolite or antifungal bacterial compounds. We also looking at them as well, but these are still, we just started this recently, and we basically have no data yet. I will be happy to let you know how that go later on. And the third study, which is probably something that more toward the biopesticide, this is where we're trying to search for biocontrol agents. So in general, biocontrol agents are refers to group of organisms that can have or enhance defense against pathogenic microorganisms. So biocontrol, they could attack the pathogen directly, or they could also compete with the niches where they had to colonize. They could also induce the plant defense through induced systemic persistence through phytohormone signaling pathway, for example. And some of them really have like a combination of different effects. And previously at Erie, since the 1986, really long time ago, and up to 2003, there were a number of studies done in the group that were time of Dr. Tomel as a division head for plant pathology and entomology here at Erie. And he have led this effort for the first time, trying to isolate microbes from different sources that have many microbes associated with seed, and see if they could have any anti-pathogen effect. And in total, we have through that period of time at Erie, we have now a collection of 163 native Philippines biocontrol agents that were isolated from seed from different regions in the Philippines, and they are mainly providing the biocontrol effects against either sheep-like or against leaf blast, brown spot, and especially also nematode or Bacanese or sheet rot. Those are also challenging diseases since we do not have a genetic solution for it. So when I came to Erie, looking back at this collection, I really would love to revise them. I really want to be able to continue some of this effort. But the reason for why that was so for a while is that biocontrol, as we know that they are microorganisms, they are living organisms, so they're challenged in terms of its application, and there are a lot of question in terms of its effectiveness under field conditions. With the farmers, it's a slow effect, so it's not that favorable for the farmer to use, and also since the effects vary so much, there are already a great number of studies showing, including my study during my PhD, showing that if we have a microbial consortia, a group of them, they can compensate and stabilize their effects under field condition. So since then, there are also a lot of different study. I think you are quite familiar with that as well. The people suggested a strategy to assemble this called synthetic community. There is top-down methods, but also bottom-up methods. This is an example for a diagram of how the top-down method look like. So for example, you can have a plant being affected by the pathogen, and then you isolate the whole microbial community and then re-inoculate it again, and then you have subsequent pathogen challenges over generation. So this is quite for help. And over the generation, the plant itself will be able to select the microbes that will help them defense against the pathogen. So these are also soil suppression effects have been shown for many different cases before. So this is one way of looking or identify a group of microbes that could be useful. Another approach is like bottom up method, where you do a lot of sequencing effort to find a correlation of a group of microbes to like enhance disease resistance. And then since you'll be having idea of what are those microbes, you can really selectively culture for them on medium and try to reassemble that community that you see that could be associated with these disease resistance, and then you can test them. Another newer approach which we are trying to apply also here is that you could build up a big collection of microbes, and then you can do the whole genome sequencing of that, and then use machine learning or artificial intelligence to actually try to assemble the community. And it's just like try and error, and as more number of data and try you have, the model will be better, and you'll be able to predict which community will be likely to work. So with those, with the same old question, like which are the beneficial microbes, but we are trying to apply a new approach so that we can quicker identify a synthetic community. So these are some of the recent efforts. So from our group now, we're really looking for searching for native, locally adapted microbes, and we expanded to not only bacteria but also fungus, and especially for endophyte, because endophyte have a lot of the hosts have a lot of control over endophyte, unlike with soil or soil microbes. And we also isolate and collect microbes from different leaf and different tissue. We can conduct antagonistic study to see whether they provide any effect. We apply the whole genome sequencing trying to make a synthetic community. And this is an example of this, the place that we have. And also last year when we did a field trip in Mindoro, we just saw this phenomenon where you have a heavy blast infected field. The plants are really bad. You can see here on the right side, but you have some plants that are remaining quite healthy. So we took out those plants and asked whether they have a better microbiome that could help them to withstand those diseases. In total, we have now a collection of 303 new isolates. They are 242 bacteria endophytes, 61 of them are fungal endophytes, and 23 of them showing antagonistic effects against magnetothiorizis that's causing rice blast. So yeah, in summary, just to sum up that the current data we have for these three main research question on microbiome, asking the question of whether rice cultivation practice have any impact, where we study specifically nitrogen management, but in fact we also study the method where people use for reducing greenhouse gas emission, like adding charcoal into the field, AWD, alternative wet drying system, how that changed the microbes and how that also correlated with reducing greenhouse gas emission. And then the second one, asking the question of what would be the gene in the host that could motivate that association with beneficial microbes, so that we can in future breed for a better variety. And there we focus mainly on defensive genes. And the third questions were about looking directly to source for the beneficial microbe and try to build a synthetic community, where we have some effort into that. We've been increasing our collection, and still we had to characterize them. So with that, our goal is, by answering those three main questions, we will be able to motivate the or engineer the whole genes, but also the microbial community itself is directly through introduction of the new biocontrol agent, or changing the environment toward favoring the beneficial microbe community. So so that we can have a better stress tolerant variety, increasing disease resistance, also increasing nitrogen fixation, so we could reduce the use of nitrogen fertilizer, and also reducing methane emission. Yeah, with that, I would like to conclude and would like to acknowledge my team members. I have a wonderful team who are experts way more than me. And I have especially IA. IA here is leading all of the microbiome and beneficial microbes effort in our group. And they is working on the bioinformatics, trying to dissect the relationship of the microbial community and the trait of interest. And I have also a lot of students, and especially undergrad students, who've been helping, especially Kat, Aside, Jenny, Martin. Those are the students who involved directly in the isolation of new beneficial microbes. And yeah, thank you very much for your attention. I can't see the time. I'm not sure if I really run out my time already. But if you have any question, please do not hesitate to ask me. Thank you.
Thank you so much, Dr. Van, and for a very interesting talk. And it's such a eye-opener. We all do realize that we need to be very holistic in our approach. But the kind of three-pronged approach that you have taken to manage the diseases of the rice plant is really commendable. So the floor is open for the questions. If you have any, I could see that there were some questions in the chat itself. So we can take that one by one. So, Mr. Juan Chan, would you like to repeat your question, which is put in the chat? So, the question is like the data shown is only for a single season party. He's just asking for that.
Yeah, that's why as I mentioned, that was just the first single season, and we have 2 more seasons to analyze. Yeah.
Thank you, Dr. Van. If there are more questions, we'll be happy to.
Just a minute. Can I? This is Dr. M.K. Naik, plant pathologist from India. Thank you, Dr. Van, for giving a very good account of rice diseases, especially how to manage with microbiome. Okay. Yeah, I could. You have been trying to tell 3 levels of how the microbiome could be used for management of diseases. One at the agronomic level, where nitrogen use of nitrogen and what is the optimum for encouraging the beneficial microbes. The other one, introduction of biocontrol agents, which can be helpful in mitigating the pathogens. And in between, you also mentioned a breeding, identifying a breeding program to encourage the microbiome, which make the plant healthy. I was wondering, are there any really programs tailored to identify a breeding program where it could target the encouragement of a specific beneficial microbiomes in the rhizosphere or phyllospheres? Any examples or breeding programs have been achieved on these lines? Otherwise, they are all generally, we consider a good resistant variety is always free from pathogens, and naturally there is a dominance of beneficial microbes, right? But otherwise, is there any targeted breeding program to encourage the beneficial microbes, keeping them in view?
Excellent. Thank you so much for summarizing my 3 really major point. Yeah. And I'm really glad that it's passed through the message. And you are really right. You're absolutely right. We really need to have kind of an effort in terms of the breeding, but I think right now our breeders are not there yet. And first of all, the number of whole genes that are known to have an impact on beneficial microbes is really few, to be honest. So we have not there to be able to tell the breeders these are the genes that you should breed for. And also what type of a version of that genes, because they also have different haplotypes. And they need to know what version of that gene they should breed for or they should select for. So we're trying now from our hand. I have not showing another approach that I'm right now looking for beneficial microbes and then basically look in questioning the plant what are the genes that they need to recruit this microbe. Okay. And then the other way I'm trying to do is a untargeted approach. So we also conducting genome-wide association study to see what are the gene linked to the microbial community, and then we are characterizing one by one. And yeah, we are not there yet to be able to have our breeders, but I hope with the community effort, we be there.
Yeah. I agree that you have given a good list of almost around 60 number of endophytes, right? Out of which, how many of them have been utilized for commercial application in the rice field? Endophytes, they
Yeah.
are the ones generally.
Yeah, none of them. I can
None
help.
of-
So, as I mentioned, it was stopped in 2003. And I think it's coincide with the time where the microbiome, whereas it's a singer, is not showing that consistent effect in the field. So at certain time, there were not a favor, like there are products out there, and then farmer doesn't like to use that. And then again, back to the question of, okay, we need to have a synthetic community. And that's why we need to go back again and see which one we can put them together to be able to produce to have a more stable effect under field condition. So unfortunately, that none of that has been commercialized. No one have been using them. That's why I feel quite pity, and we really want to restore those. And we have in the stock, and we are revising them for reevaluating them. Yes.
Yeah. Thank you, Dr. Van. I think this has answered the question. I see some more questions in the chat box. And
I would like to ask a question.
yeah, sure. Please go ahead, Mr. Mosi.
Thank you so much, Ms. Wen, for having such a kind of what a nice presentation regarding to the current scenario of rice production. Basically, I'm from Pakistan and from Sindh. Here we have a specific area where the most of the land are under rice cultivation, and these kinds of things are being phased. So, as Dr. Naik uh, ask about the breeding programs. Beside that, as we have challenges of climate, we have to go towards the climate resilient varieties. Beside that, it's an uh, very big side to improve. But on the farmer side, implementing the microbiome friendly rich rice cultivation practices, we have to go over there, like soil health improvement, conducting soil microbial analysis, and understanding existing microbial diversity, like usage of biofertilizers, organic amendments, and reducing of the harmful pesticide. Likewise, minimize excessive chemical fertilizer that harm the beneficial microbial, and reduce our use of fungicide and pesticide to distribute microbial communities. Or we can implement the sustainable irrigation techniques like alternate water and drying to prevent the anaerobic condition that favor harmful microbes. Because in areas before this side, from agriculture or government side, I was in a pesticide company, so where the farmers are very associated with the pesticides. Likewise, when they start preparing the soils, they start approaching the pesticide from post post cultivation pesticide after sowing of crops. So we need to go on this side as well to reduce pesticide or sown practices to enrich the microbial activities.
Thank
Yeah.
you. Yeah. You have some comments over there, Dr. Van?
Oh yeah, I just totally agree. As you said, we need to have more sustainable way of cultivating our rice. As I also observe or experience by myself, as my parents are also farmers, rice farmers. And we can clearly see how the soil is being drained because of too much use of fertilizer and pesticide, where you see the nutrition uptake of plants is way less compared to the earlier time when I was child, where we just have to introduce so little of fertilizer, our plant were so happy already. But nowadays you have to have ton more of fertilizer in order to obtain a similar effect. And a lot of not only microorganism which we don't see, but even larger macroorganism which are usually living under soil or under rice field are no longer there, or mostly at that. So it's very sad situation when I go back to my village and see what is happening. And really I look for a way that we could restore the system, restore our soil to much more sustainable way of cultivating our rice. Thanks.
Yeah, thanks. And I see Paul Taylor. His hand is up. Would you like to ask your question, Paul?
Yes, I'm very interested in this area of work, and well done. It's identified a lot of useful microorganisms that can be applied. My question is more around the application, and that leads into the commercialization aspects. But have you done the research into the most appropriate and sustainable ways of applying microorganisms, particularly to the root zone, that will then actually have activity and action? Because that, to me, is the last frontier in biocontrol and these sort of areas, is the application and the sustainability of the microorganisms within the soil environment. Some comments on that, please?
Yeah, that's how, thank you very much for that question, because I think that was one of the challenge, right? That why the biocontrol agent were having a hard time to be applicable in a larger scale and more stable. So with the microbes here at Erie, we have not done to that step yet. But previously, when I did my PhD, we were really advocate or testing different way of introducing, and we found that if you introduce the microbes earlier on when plants are germinating, when it's like feeding your infant with the first milk, then the microbes could be uptake more efficiently, and they could also stay throughout the growth duration of plants. But it's also depend on the microbes that can stay longer. And I intend to test a similar approach with rice, because for rice, especially for transplanting rice, we have periods of time where they have in the seed bed system. So that could be a good way of inoculating our microbial consortium at the very early stage. But
Thank you.
So I see one more question in the line. You get to speak out your question.
The Nicospora, I think we haven't encountered, but we still have a lot of them and not characterized yet. So we are still characterizing our collection right now. So I will see if Nicospora is coming. Pavati says he used Pseudomonas fluorescent 1% with the in the party field, and it's worked well for blast fly and sheet rot. Yeah, and yeah, we also have them in our collection, and I also emphasize on the need of using native and locally adopted microbes, because similar to us as human, it's the same species. We have so many variants. The one become more adapted to certain location climates. So that's why I really focusing on getting the microbe from where it's needed and reintroducing them. Yeah.
So, Dr. Van, I think that is a very nice approach to rely on the native isolates. I had one question over there, since you're doing extensive study, even with the suppressive soils and even bioagents which are present in the microbiome of rice and which are very effective in keeping the diseases low. So do you also have any commercial product, and does the industry approach you to get those strains from you and make a commercial products out of that? Because it will benefit the farmer to a very large extent as they are very well researched strains.
Yeah, so we would be really happy to if someone is interested in taking them forward, because they are coming here from the Philippines, and we would love to have them being utilized by the farmers. So we have no problem, or we actually really welcome if there is any interest of utilizing them. Yeah.
Yeah. So just an extension to my question, I see that with Philippines, there are almost 150 biopesticides which are registered nationally. Out of them, majorly they are for rice. But do you think there are enough of availability for the farmers to use, or is there any other different methods that the country is actually utilizing to make these products available to the farmers?
Yeah, so my question back would be whether those products those microbes are really the microbe being obtained here, or whether they are really being deployed where they should be. That could explain why it may work in some place and then doesn't work in another place. So microbial solution similar to pathogen solution, as we do, we always have to characterize their population in order to know where to targetedly deploy our gene. In this case, where to targetedly deploy our biocontrol agent. That one thing. Second is whether those products are taking in consideration of the synthetic community, how they are working together. That would be able to enhance their efficacy.
Yeah, I do agree. Thanks.
Yeah, so that's that. I hope I work that direction and be able to provide alternative solution or better solution. Hopefully, I don't know.
Yeah. So I would like to ask the house if you have some more questions. So there's again something on the chat that I'm not sure in the other country, but in Malaysia, rice farmer also uses a lot of herbicides during and off season. Maybe herbicides have been taken into consideration, and also chemical pesticide during the season. And how about salinity of water, which is becoming a problem too? I think these work on impact of cultivation practice on microbiome. and has to continue for long term.
Yeah, I think we still need to have more study. I think there were already a recent review with summarizing all of the different chemical application, how that impact on the soil microbiome, and they really show that is having a long-term impact. Yeah, I think yes, we have to, especially when a new product coming out. Now we know that we need to take care for not only the plants, but we have to take care for the microorganism around in or present in those environments. So that should be considered when approving any new product.
Thank you, Dr. Van, for a very insightful talk and very interesting interaction. Thank you to the participants as well for very active listening, and we had very productive discussions today. So with this, I hand over to Darshika. Darshika, would you like to close the meeting?
Yes, Dr. Malvika, thank you very much. So we would like to wind up today's session, and before we finish, I just wanted to take a moment to express our sincere gratitude to all of your contributions today, and a special thank to Dr. Bond for her excellent presentation. And it was truly insightful, and also a big thank to Dr. Malvika from CABI for joining us to moderate the session today. And I really appreciate the active participation of all the members in the discussion and question and answer session. And I would also like to thank my colleagues, APARI colleagues, for their support. And we will keep you updated on the next AppCop session soon. And thanks again. We look forward to see you in the next session. So thank you, everyone. Thank you.
Thank you very much. Bye.
Thank you.
Thank
Take
you,
care.
everyone. Thank you for a wonderful time.
Thank you very much.
Bye bye.
Thank you. Bye.